Hey kids, Smath here. And I wanted to take a minute to talk to you about a topic that we don't get to cover too well in class, but deserves a few minutes of recognition here. And I'm going to share here, this is called Beers' Law, and it falls into the topic of spectroscopy. Spectroscopy is basically the study, spectroscopy sorry, is basically the study of matter, in our case, a solution, interacting with the electromagnetic spectrum. For lack of a better word, light. How does light affect with solutions? And in our case, what we're going to do is shine a beam of light through a solution and measure the absorbance of that. And the outcome of this is what's called the Beers-Lambert Law. And Beers-Lambert Law makes, this is one of the labs that we're supposed to do. And it just is, it's very timely. So what happens is we usually have some sort of spectroscope. I've got these little guys here. Let me swap out screens here real quick. I've got these little guys called spectroscopes, and it operates usually flat on the table. And what you can do is adjust the wavelength of light that gets shined through here. And this is going to be visible. There is spectroscopy that's ultraviolet, visible, and infrared. We stick to mostly visible within our spectrum, and they use these little plastic containers called cuvettes. And you can see that on one side of the cuvette, there are ridges, and on the other side of the cuvette, it is clear. And if you notice, I'm holding it on the side with the ridges. And so what happens is I take my cuvette, I turn it so that the clear sides are going to be in alignment in this direction. And when I push it down, this will shine a light through and measure how much light is absorbed or transmitted by a colored solution substance. This only works with substances that have pigment to them. So a lot of transition metal substances work like this. But this is how we collected. This is how I collected this data. And so I did this the other day in class during a break, and I made the different solutions, pushed them through, and it gave me the amount of absorbance that these solutions had. And now let me go back. And so when I take those data points and they plot, what I plotted in this was, it's kind of hard to see, the concentration, which I knew and I controlled. I made different concentrations of 4, 6, 8, 10, and 12 molar. These are 10 to the minus fifths or sixths, I forget which ones. And we measured those at a set absorbance of 445. So my solutions were relatively red, which means we're going to want to measure those at the opposite wavelength, measuring them at a blue. And this told me the absorbance. And the spectrometer actually ends up plotting absorbance on the Y and concentration on the X. And this is what's called a standard curve. Okay. And from that standard curve, we can measure. Now we know what the absorbance will be of a known solution. And so if we create an unknown solution, so what happened in ours, the reaction we had was very simple. It was Fe2 plus SCN minus. This makes an Fe SCN plus ion. And this ion has a relatively reddish pigment to it. And so we were able to measure the different pigments to it. Well, what's kind of unique is I can change my concentrations of Fe my concentration of SCN, and then plug in my solution into my spectrometer, okay? And it's going to measure, let's say, it measures the absorbance at about 0.42 or whatever. I take that over, I can take that down, and now it tells me that my concentration of FeSCN is 0.000412345 So all I'm doing is using my standard curve to measure the absorbance, indirectly infer the concentration. I could also calculate that with my formula, with my equation, y equals mx plus b. I'm not going to in this case. My estimation is close enough. But if I know going in that, excuse me, this concentration was known, this concentration was known, this concentration was known, we mixed them together, and we found out that the concentration of FeSCN was there. We can now calculate the KEQ by putting the concentration of FeSCN plus over the concentration of Fe over the concentration, now that's a 2 plus, yes, over the concentration of SCN minus. And from this, using our spectrometer, we can calculate the KEQ for this complex ion formation. And that's kind of unique. This is one of the labs, and the board likes you to see these labs. Now, the other thing that the board likes you to see and just be familiar with, this isn't mastery by any means, but this is, they want you to be aware of Beers-Lambert law, which basically is A equals EBC. And these all have different players. Let me get some room here. A is going to be my absorbance. That's just what I measured over here on the y-axis. E is going to be the molar absorptivity. Absorptivity. It's how well a substance, a solution, interacts with light at a certain wavelength. We don't really need to worry too much about that. B is the pathway length, just called the path length. What B is the distance basically from the start of my cuvette to the end of my cuvette. That's what this little square plastic test tube jobby is. This is called a cuvette. And so the pathway length is the length of how far across this is. It's usually 1 centimeter. That's a common, this is just a common sized cuvette. Buy them by the thousands. They're cheap and disposable and easy to use. So that's B, and C is of course our last player. That's the concentration. And so from this, we can see that absorbance and concentration are directly proportional. When one goes up, the other goes up. When one goes down, the other one goes down. Because we're not going to change what substance it is, which isn't going to change the molar absorptivity. And we can't change the length of the cube. The cube is set. So there's nothing we can do there. So those are my variables. You won't be asked to do any calculation with the Beers-Lambert law. They may just ask definition-y things about it, that absorbance and molar absorptivity, path length, and concentration. So that's your background, and that's why it's one of the labs that's recommended. Is they want us to create a standard curve, and from that standard curve, they want us to then make a measurement of an unknown, trace it backwards, using the absorption, get the concentration. That's the lab side of it. What does this look like in terms of practice? I have 3 practice problems that I pulled off of the AP website. Don't tell on me, okay? What it says is they gave us a standard curve here, and it says a student made the standard curve, and which of the following most likely occurred in the error? And it's basically going to be why would one data point, they're asking, why is this data point low? Why is the error in that plot off? And the answer is very simple, because what would cause the absorbance to go down would mean that the solution was too dilute. And so in this case, there was distilled water left in the cuvette. So those of you that are just looking for, what do I need to know to get the spectroscopy question right? Watch out. The question always makes reference to the cuvette and that there was some water left in the cuvette. As a matter of fact, if I hold this up, you can see there's actually a little bit of water left in there. It's hard to get all of it to drain out. So that is a very common error that's associated with these. If there were a few drops of the 0.1 molar in the cuvette and we were wanting to measure 0.50, that would be more concentrated. That would mean my dot would actually be higher. That's what B would look like. A looks like that. The student used a cuvette with a longer path length for the cuvette used from the other standard solutions. Well, that really can't work. You'd have to change the spectrometer. So that's just not a good answer to try to do. And D, the student didn't run a blank. Now, a blank is when you run pure water. You just put a cuvette with some water in it to say, by the way, this should be 100% transmittance, and you're supposed to do that quite commonly. That wouldn't make it register low. That would just be like re-zeroing the machine. So if you're wondering what causes plots to be too low, distilled water left in the cuvette. What causes plots to be too high? Higher concentration. Okay. Here's another one. This may be the same one. They had similar questions. Okay, and this is the same one, so we're not going to worry about that. Here's the third one. Using a spectrometer, a student measured the absorbance of 4 solutions, CuSO4. So again, now we're measuring a blue solution instead of a red solution. No biggie. The collected data, which of the following is the explanation for the discrepancy in trial 4? So what they're saying is trial 4 is a little bit off. Okay. And so they're saying the solution was at a lower temperature than the solutions of the other trials. We haven't talked about temperature. It has an effect, but not one that we're going to go into. So it's not very much use. The measurement was made using a different spectrophotometer with a longer path length. Could be, but if it has a longer path length, it's going to have a different absorption, and it's going to have, it's going to adjust for that absorption. So they're going to go up and down proportionally. So that's not the right answer either. And C, the solution was saturated and the flow of light through the solution was restricted. If that's the case, that would have caused the measurement, to be too low. This one would cause a change that the cell length, the cell path changed and the absorption changed. So that's not going to have an effect. Lower temperature does not mean, lower temperature actually ends up meaning nothing about absorptivity as long as your solution, as long as it dissolves and goes into solution. And D, the last one, the concentration solution was actually too low. Ding, ding, ding. So quick takeaway. Beers-Lambert law, absorbance is proportional to concentration, directly proportional to concentration, and what causes concentration values or absorption values to be too low is dilution, and causing them to be too high would be having too high of a concentration of stocks. And so what we find is it's just a tool for measuring wavelength of light. And in the end, when it does so, we can use a standard curve to get concentrations and use those concentrations to figure out unknowns. I think that's all we need to know about Beers-Lambert law. It may show up for one question, it may not, but I'm Smath. I've given you a brief 20-minute rundown on it, and I hope this video helped.